I'll discuss with you the circuit symbols and the conventions associated with the MOSFETs. Now, over here, if you see down at the bottom, you have an Nmos device. Why it is Nmos? Well, you can see that its channel is consisting of the negative charge particle electrons, okay, which are responsible for the flow of current from source to drain, given the direction of this current. So if the channel is consisting of positively charged carriers or holes, well, then it's a Pmos, okay, with the direction of current reversed. Now, how do you relate this device with the circuit symbol? The first thing to show is to see over here is you don't see any substrate, okay. Now you can say that this is a 4-terminal device. You have a gate, you have drain, okay, and this terminal is connected to the n-doped region of semiconductor. Then you have a source, which is again connected to the metal is connected to the n-doped region of the semiconductor. So you have the third terminal, and then there is a fourth terminal over here. Over here you see only 3 terminals. So you have source, you have drain, and you have gate, okay. And the same thing goes for the parts B and C. It's a 3-terminal. I mean, yes, it is a 4-terminal device, but it becomes redundant to show this substrate, okay. The substrate or the semiconductor is connected with the source, okay. The substrate or the semiconductor is grounded with the source, okay. So it's at the same potential of what the source has. So it becomes redundant to show the 4-terminal, okay. So let's consider a 3-terminal device, and let's try to understand this 3-terminal device symbol and the convention associated. So the first thing is, you see the gate is consisting of a solid line, okay. It's not a dotted line like this. The solid line shows the metal. This is the metal. This metal could be aluminum, it could be polycrystalline highly doped silicon, but it's metal, okay. It could be gold, it could be titanium, okay. It's a metal. So this metal is a solid line in all 3 symbols. Then comes the perforated or the dotted line over here, and this represents the channel, okay. Well, basically I'll say that this represents the enhancement mode of MOSFET. There is another mode known as depletion mode, which we are going to discuss in the next video, but for now you need, for that kind of fabrication in which you need external supply with the gate, okay. Over here you see, since this is an Nmos, and if you recall in the previous videos, we had uh, positive positive gate voltage, because your threshold voltage is negative. I mean, the biasing as such is as such that you are accumulating positive charges over here, okay. The metal is going to have positive charges, and the bottom plate of the MOS capacitor is going to have negative charges, which you see over here, okay. Because this negative is going to come over here, and it's going to attract some holes, okay, at the substrate body, down at the substrate or the semiconductor bulk body. And then you have some minority carriers, okay, which are going to form the channel, and they are going to because this is negative side, so it's going to attract those positive holes, and then some minority carriers are left behind, and these are basically shifted upwards, and they are of the bottom plate of the capacitor. This is your MOS capacitor, this is oxide, okay. And if you see in the symbols, there is a small gap, which is a small gap shown between the metal, the gate metal. So this is the gate metal, this is your gate metal, okay. And then you have these perforations. So this is the difference, the separation represents the oxide in all 3 symbols, okay. And this dotted line is representing the channel. This is the channel, okay. And this channel is being created by an external biasing source. You need an external biasing source. It is positive if it is Nmos, okay, because you need the minority carriers of the substrate. Substrate is p-type, which is majority carriers are holes, okay. So you have the channel is consisting of the minority carriers in the substrate, okay, which are negatively charged particles, electrons. So so you need biasing. The thing is, you need biasing to create the channel, and thus to conduct the current from source to drain. So these dotted lines are representing the channel, And if you see, there is another mode of MOSFET which is known as, which is famous as depletion mode. This is enhancement mode, and then you have a depletion mode MOSFET. The fabrication of that mode is as such in MOSFETs that you fabricate the channel with the drain and source terminals. Okay, so the channel is already fabricated. You don't need an external supply. In that case, this becomes a solid line. Okay, don't confuse that these are depletion modes. These all are enhancement modes. Just the conventions are a little bit different. You see the in part 8 says this is the conventional circuit symbol. Okay, so this dotted line is your channel. Then you have the oxide in between. So there's a separation between the gate, between this gate and between channel. You have uh, this this much thick oxide. So there is separation. Okay, so this solid line is gate. So this is following in all the three conventions, but in B it's a little different. You have a solid line over here. It shows the circuit symbol that will be used in this text, okay, for more clarity. So the author is more favoring the, part, the middle symbol for MOSFET, okay. So not much of a difference, but this is how the convention is. The part A is the conventional or traditional circuit symbol for MOSFET. Uh, so C is a simplified circuit symbol used in more advanced texts like journal articles, people who are publishing in microelectronics papers, journals, conferences. They sometimes use this the last circuit symbol, to represent MOSFETs in their circuit diagrams. The only difference in this circuit diagram, all three are, three. They're representing this as a three-terminal device. Okay, the idea of having drain at the top in all three is that drain is at a positive potential with respect to source. Okay, so the drain is more positive. Drain is more positive. You can see that. Why? Because you are making this PN junction at the drain side reverse biased. Okay, so VDS is positive over here. So what's going on is that you are having a positive battery connection with the drain, negative over here, and this battery is basically this VDS is responsible for the reverse bias of this junction. Okay, this junction I'm talking about. So as you increase VDS, you remember in the last videos, you reach towards saturation, you pinch off the channel, okay, because this is going to increase and this is going to increase with this side as well, and the channel is going to taper off, something like this happens, and you reach the saturation. Okay, so basically, and anyways, VD is positive with respect to the body, the substrate. So drain is shown as positive with respect to the source. It is drawn in the north, in the upward direction. Okay, and then you have okay, in the conventional symbol, you have the current direction. This arrow is showing, no, not this arrow. You have the current direction in the conventional. Oh, sorry, over here, ID, and the conventional current direction is from drain to source. But in practice, given this biasing, it looks like that the particles enter from source, and then these negative particles are attracted to the positive terminal of the battery. Okay, but since the conventional current is the other way around, so that's how the arrow is shown. The conventional is from drain to source, but actually it's from source to drain. Okay, in Nmos, the direction of the flow of charges, physical flow of charges, is from source to drain, but conventional is taken the other way around. So that's the direction of the currents. Okay, in all three circuit symbols. So um, the last thing that remains to discuss is this arrow. Okay, so you have the bulk body. This B is the bulk. So this, what it shows is the direction of the PN junction it forms with the bulk. This is your bulk body. Okay, this is your semiconductor, or what you call this as the substrate. Okay, so the direction of the PN, see, this is P-type material. Okay, this is P-type material, and this is N regions. These are N regions. Okay, so the direction from P to N is like this. Okay, and this is toward the oxide and the gate. So you have this towards the channel, oxide, and gate. Okay, so this direction shows the direction of the PN junction from P to N. P to N. Okay, but in the other two diagrams, okay, which other authors, including this author, is favoring, is well, you don't have any this p-n junction direction. Um, well, you just have the current basically. You're not drawing this like from the external substrate like this. You don't have this over here or here. Okay, it's not shown over here. So anyways, so the current is shown from drain to source, which is the conventional. All right, and there's no even arrow in this the last circuit symbol, which is preferred in the recent publications. Okay, so the conventional circuit symbol for n-channel enhancement mode MOSFET is shown in 12A. So you have seen this is conventional. You have gate and you have channel separated by an oxide. Okay, this solid is gate and this perforated line or broken line is your channel. All right, then from P to N is the direction shown from the body of the semiconductor towards, so this is P to N, this is P to N junction, so that's the arrow. And then you have three-terminal device and the conventional current is from drain to source. The vertical solid line denotes the gate electrodes, right? The vertical broken line denotes the channel, which we talked before. The broken line indicates the device is enhancement mode. The separation between the gate and the line represents the denotes the oxide that insulates the gate from the channel. So it's this oxide which I have shown before. The polarity of p-n junction between the substrate and the channel is indicated by arrowhead on the body of the substrate terminal. So this arrow, the direction of P to N, okay, p-n junction. So the polarity of p-n junction, this is polarity of p-n junction between substrate and the channel. So it's like this. So this is p type substrate and this is n channel. That's the polarity represented by the by this arrow. All right, this arrow. The direction of the arrowhead indicates the type of the transistor, which in this case is n-channel device. The symbol shows a four-terminal structure of the MOSFET device. Well, yes, you have a four structure. Okay, we don't have any second opinion of that. Yes, it is a four-terminal, but it becomes redundant to show this terminal because this terminal is at the same potential as the source. So you just show this by one source only. You don't need to show the bulk. So it is assumed that the source and the substrate terminals are connected together. Explicitly drawing the substrate terminal for each transistor in a circuit becomes redundant. Okay, this makes the circuit symbol actually more complex. So the idea is not to include the substrate. So instead we use the circuit symbol for n-channel MOSFET. Instead we use that. Actually, the author is saying that in your text, Donald A. Neiman. So he's favoring this 12B. Okay, this is less complicated. So we'll be using this the circuit of B as a conventional symbol in this text. Okay, for later analysis of MOSFETs, DC analysis and AC analysis. So in this symbol, the arrowhead is on the source terminal and indicates the direction of current. The direction of current for n channel is out of source, but the conventional is the other way around. The conventional is from drain to source. Otherwise, yes, it is from source, and it's like the negative charge is being attracted to the positive terminal of the battery. The current, but the conventional current is shown the other way around, so drain to source. Okay, so drain to source over here. Otherwise, it is out of source. Okay, so it says the same thing in advanced texts like journal articles or in conferences. The people they refer to the circuit symbol of n-channel MOSFET shown by 12C, okay, in which you don't have any arrows, okay, out of the source. You don't have this nothing over here. No bulk p-n junction polarity is shown over here. So this is a simple structure. No perforations over here. No perforations of the channel. So, but yet does it, and it still represents that n-channel n-channel enhancement MOSFET. So the gate terminal is obvious, and its simplicity is that it's implicitly understood that the top terminal is a drain, bottom terminal is the source. Top terminal in this case, drain is usually positive, is more positive than the bottom terminal. The potential of the voltage of the drain terminal or the upper terminal is more positive. Yes, it is more positive. You see the drain is positive. Drain is positive with respect to your source. Okay, so the less positive is at the bottom, the more positive is at the top in the north. Okay, so this is the understanding of the circuit symbol. Now let's talk about the Pmos. Okay, so now we have Pmos device, and if you can extrapolate your understanding of what I have explained, everything goes in reverse. The first thing to notice is that Drain is at the bottom, south is at the bottom, source is in the north, or in the, because source is now, the source is more positive, the source is more positive now with respect to the drain. You see the drain is now connected to the negative terminal of the battery. The negative terminal of the battery is connected over here. So this drain is at a lower potential. So the first thing you notice in all three conventions, in all three circuit symbols, you have this source more positive, drain is less positive. Okay, and then again, once again, this solid line is representing your gate. Okay, which is metal over here. Okay, and yes, you have the, if you recall, this VSG should be greater than, it was said that it was, should be greater than BTP, okay, because it is enhancement type, which we can see over here due to the perforated or the dotted lines. So this shows enhancement type Mosfet, enhancement type Pmos Mosfet, because your this gate voltage is negative this time, so it is going to accumulate negative charges, and you need to create the field to have a channel. It's a Pmos device, so basically your there will be holes, so P positive. So you have these holes in the, as a mobile carriers. Okay, although the mobility of holes is practically is less than the electrons, owing to the heavier size of the holes. So, but that's the conduction parameter. It's included in your parameter Kp. Okay, we've discussed before. You've seen Kp over here. This is your Kp. All right. This involves this parameter of mu p, which is the mobility. Okay. So you have this the difference of the gate and this the channel in all three convention is separated by the oxide. So here you have the separation is representing the oxide. Same scenario. Okay, gate is metal and channel is dotted in the conventional symbol. In the other symbols, there's no perforations. Okay, so just for the sake of ease of drawing and clarity, you don't show those perforations. Okay. So again, the author is favoring this second symbol that will be used in the text. So part C is a simplified circuit symbol that is used in more advanced text. So again, the other thing is that this is an N-type. So for PMOS, we have N-type substrate or semiconductor, and the direction will be from P to N. This is your PN junction. Okay, so this whole thing is your PN junction, including the reverse bias PN junctions over here, including the channel and the doped source and drain terminals. Okay, so the direction is from P to N, this direction. So it's away from the gate, oxide, and the semiconductor and the oxide interface. So basically, it's away from the channel. So this is the direction of the PN junction. Okay, right. But actually, the channel is consisting of P, and then it's towards N. N is the substrate material, or it consists of more electrons and type carriers in the substrate, right? So you see the direction of the arrows are reversed over here. Again, the conventional current direction is from the conventional is the other way around as compared to Nmos. It is from source to drain, right? So it's source to drain as shown in all three configurations. Okay, so the conventional symbol for p-channel enhancement MOSFET appears in 13A. That's your conventional. Traditional symbol. Note that the arrowhead direction on the substrate terminal is reversed from that of N-channel enhancement mode device. So the arrowhead on the substrate, yes, it is reversed. You see this over here. This is from P to N now. So this is reversed. This is the other way around in Nmos. This is Pmos. Okay. So this arrow is reversed if you remember it. This is from P to N over here. Okay. So basically your substrate was P-type and then your channel is N-type. So this arrow is reversed. Alright, so the circuit symbol again shows 4-terminal device, but the circuit symbol for PMOS enhancement device 13B will be used in the text, okay, for whenever you are going to use this as a common source amplifier or in applications, we use the circuit symbol given in B, okay, with no perforations, okay, no dotted lines, and no substrate PN arrowheads, no substrate or bulk arrowhead showing the direction of p-n polarities. The arrowhead is on the source terminal indicating the direction of current, which is for the p channel device into the source terminal. Okay, it's into the last time it was out of the source. It's the other way around. So for n channel it's out of the source. For p channel, it says it's into the source. It's into the source. Okay, so it's into the source. Okay, now so in more advanced texts like journal articles, 13C is generally preferred, and again the gate terminal is obvious, and that O symbol over here, this O symbol you see over here, this is your O symbol. This is representing Pmos device. This is Pmos O. This is the O. Okay, so this represents Pmos. All right. So this O symbol in 13C is used to indicate the Pmos device. It is simply understood that the top terminal is the source and the bottom is the drain. The top terminal, the convention is the same. The top terminal source is normally at a higher potential than the bottom terminal. Again, in this course, we will use the symbol that is shown in 13B for clarity. Okay, so we will use this the middle symbol for PMOS device in applications of MOSFETs. Okay.